Section 8.2, Ionic Bonding. When sodium metal is brought into contact with chlorine gas, a violent reaction ensues. The product of this is very exothermic reaction is sodium chloride, NaCl. Sodium chloride is composed of sodium ions and chloride anions, which are arranged in a regular three-dimensional array as shown in figure 8.3. The formation of sodium from sodium metal and chloride from chlorine gas indicates that an electron has been lost by a sodium atom and gained by a chlorine atom. We can envision an electron transfer from sodium atom to the chloride atom. Two of the atomic properties we discussed in Chapter 7 give us an indication of how readily electron transfer occurs. The ionization energy, which indicates how easily an electron can be removed from an atom, and the electron affinity, which measured how much an atom wants to gain an electron. Electron transfer to form oppositely charged ions occurs when one of the atoms readily gives up an electron, one that has low ionization energy, and the other readily gains an electron, one that has high electron affinity. Thus, sodium chloride is a typical ionic compound because it consists of a metal of low ionization energy and a nonmetal of high electron affinity. Using Lewis electron dot symbols and showing a chlorine atom rather than the Cl2 molecule, we can represent the reaction as follows. The arrow indicates the transfer of an electron from the sodium atom to the chloride atom. Each ion has an octet of electrons, the octet from sodium ion being 2s2 2p6 electrons that lie below the single 3s valence electron of the sodium atom. We have put a bracket around the chloride ion to emphasize that all 8 electrons are located on the chloride ion. Energetics of ionic bond formation. As seen in figure 8.2, the reaction of sodium and chlorine is very exothermic. In fact, equation 8.1 is the reaction for the forming of sodium chloride from its elements, so that the enthalpy change for the reaction is heat of formation for sodium chloride. In Appendix C, we see that the heat of formation of other ionic substances is also quite negative. What factors make the formation of ionic compounds so exothermic? In equation 8.2, we represented the formation of sodium chloride as the transfer of an electron from sodium metal to chlorine gas. Recall from our discussion of ionization energies, however, that the loss of electrons from an atom is always an endothermic process. Removing an electron from sodium to form sodium ion, for instance, requires 496 kilojoules per mole. Conversely, when a nonmetal gas gained an electron, the process is generally exothermic, as seen when a negative electron affinities of its elements. Adding an electron to chlorine gas, for example, releases 349 kilojoules per mole. If the transfer of an electron from one atom to another were the only factor in forming an ionic bond, the overall process would not be exothermic. For example, removing an electron from sodium gas and adding it to chlorine gas is an endothermic process requiring 496 minus 349 equals 147 kilojoules per mole. This endothermic process corresponds to the formation of sodium and chloride ions that are infinitely far apart. In other words, the positive energy assumes the ions are not interacting with one another, which is quite different from the situation in ionic solids. The principal reason that ionic compounds are stable is the attraction between ions of unlike charge. This attraction draws the ions together, releasing energy and causing the ions to form a solid array or lattice, such as that shown for sodium chloride in figure 8.3. A measure of just how much stabilization results from arranging oppositely charged ions in an ionic solid is given by lattice energy, which is the energy required to completely separate a mole of solid ionic compound into its gaseous ions. To get a picture of this process for sodium chloride, imagine that the structure shown in figure 8.3 expands from within, so that the distances between the ions increase until the ions are very far apart. This process requires 788 kilojoules per mole, which is the value of the lattice energy. Notice that this process is highly endothermic. The reverse process, the coming together of the sodium and chlorine to form sodium chloride, is therefore highly exothermic. The delta H is negative 788 kilojoules per mole. Table 8.2 lists the lattice energies of sodium chloride and other ionic compounds. All are large positive values, indicating that the ions are strongly attracted to one another in these solids. The energy released by the attraction between ions of unlike charge more than makes up for the endothermic nature of ionization energies, making the formation of ionic compounds an exothermic process. The strong attractions also cause most ionic materials to be hard and brittle, with high melting points. For example, sodium chloride melts at 801 Celsius. The magnitude of the lattice energy of a solid depends on the charges of the ions, their sizes, and their arrangement in the solid. We saw in Chapter 5 that the potential energy of two interacting charged particles were given by E sub L is a constant times the two charges divided by the distance apart. In this equation, Q1 and Q2 are the charges on the particle, D is the distance between their centers, and K is a constant, 8.99 times 10 to the 9 joule meters over Coulomb squared. Equation 8.4 indicates that the attractive interaction between two oppositely charged ions increases as the magnitude of their charges increase as the distance between their centers decrease. Thus, for a given arrangement of ions, the lattice energy increases as the charges on the ions increase and as their radii decrease. The magnitude of lattice energy depends predominantly on the ionic charges between the ionic radii vary over a limited range. Electron configurations of ions of the s and p block elements. We considered the electron configurations of ions in section 7.4. In light of our examination of ionic bonding, we'll continue with that discussion here. The energetics of ionic bond formation helps explain why many ions tend to have noble gas electron configurations. For example, sodium readily loses one electron to form sodium ion, which has the same electron configuration as neon. Even though lattice energy increases with increasing ionic charge, we never find ionic compounds that contain sodium 2+ ions. The second electron removed would have to come from an inner shell of the sodium atom, and removing electrons from an inner shell requires a very large amount of energy. The increase in lattice energy is not enough to compensate for the energy needed to remove an inner shell electron. Thus, sodium and the other group 1 metals are found in ionic substances only as positive 1 ions. Similarly, the addition of electrons to nonmetals is either exothermic or only slightly endothermic as long as the electrons are being added to the valence shell. Thus, a chloride atom easily adds an electron to form chloride, which has the same configuration as argon. To form a chloride 2- ion, the second electron would have to be added to the next higher shell of the chlorine atom, which is energetically very unfavorable. Therefore, we never observe Cl2- ions in ionic compounds. Based on these concepts, we expect that the ionic compounds of the representative metals from group 1A, 2A, and 3A will contain cations with charges of +1, +2, and +3 respectively. Likewise, ionic compounds with the representative nonmetals in groups 5A, 6A, and 7A usually contain anions with charges of -3, -2, and -1 respectively. Transition metal ions. Because ionization energies increase rapidly for each successive electron removed, the lattice energies of the ionic compounds are generally large enough to compensate for the loss of up to only 3 electrons from atoms. Thus we find cations with charges of 1, 2, and 3 in ionic compounds. Most transition metals, however, have more than 3 electrons beyond their noble gas core. Silver, for example, has krypton 4010 5s1, an electron configuration. Metals of group 1b, copper, silver, gold, often occur as +1 ions, as in copper 1 bromide and silver chloride. In forming the silver ion, the 5s electron is lost, leaving a completely filled 4d subshell. As in this example, transition metals generally do not form ions that have a noble gas configuration. The Octet Rule, although useful, is clearly limited in scope. Recall from our discussion in section 7.4 that when a positive ion is formed from an atom, electrons are always lost first from the subshell, having the largest value of N. Thus, in forming ions, transition metals lose the valence shell s electrons first, then as many d electrons as are required to reach the charge of the ion. Let's consider iron, which has an electron configuration of argon 3d10 4s2. In forming the iron 2 plus ion, the two 4s electrons are lost, leading to argon 3d6 configuration. Removal of an additional electron gives the iron 3 ion, whose electron configuration is argon 3d5.